is the video for section 7.4 in BC Calculus on arc length. So this is a BC only topic. It's not something covered in the AB curriculum. So that means that for all of us watching this video, this is new material that we need to pay attention to. So we're just going to start with the graph of sine of x here. And if I wanted to know the length of the curve y equals sine x from 0 to 2 pi, I mean, you kind of think about finding the length of that. You could take a piece of string, and just trace it or run the string along the curve, and then take that piece of string and lay it out against a ruler, and you see how long the curve is. So that's the whole concept of arc length. Now, we can't really do that, though, all the time. You can't walk into your AP test with a piece of string in your pocket that you're going to use to measure arc length. Plus, we're not really measuring in inches or centimeters or anything like that. We just want to know, basically in units terms, how long the curve would be. So what we could do is, if this was a linear function, we could just look at the different lengths of the different segments using distance formula and then add those lengths together. But being that this is curved, it becomes a little bit harder to kind of chop it up like that. So what we could do is we could divide our interval from 0 to 2 pi into tiny subintervals, find the length of each of those tiny little subintervals using the concept of like a tangent line and local linearity, and then add those lengths together. But again, that's not 100% accurate because it's kind of like with the Riemann sums. There's going to be some gaps of where it's not perfectly fit along the curve, unless you could ideally do an infinite number of little subintervals to construct into tiny little segments. So like a tiny little segment here, and then another one here, and another one here, and so on, and piece them all together, and eventually they would make the curve. But the goal is to do an infinite number of them. Well, to find the length of any one of those tiny little segments, it would be the distance formula. So it would be the square root of the change in x squared plus the change in y squared. But that would give us the length of any one segment. But then we would want to add all of those lengths together for all of the different changes in x. And we'll say from k equals 1 to infinity, because ideally we're doing an infinite number of subintervals. So doing this, as the width of our subintervals gets closer and closer to 0, because we're doing an infinite number of them, like I said, this would be like a Riemann sum. And so we could think of it as that sum, but done with respect to the change in x as the change in x goes to 0. So this, if we think about it like this and we try to work with it, would actually kind of go with me here. I'm going to go a little bit out of the box. This would become the sum of, now if I try to take this change in x sub k and put it back under the radical, I would need to square it and then put it underneath both of these. Now in doing that, my first fraction would be change in x squared over change in x squared. So that would just be 1. And then my second fraction would be change in y squared over change in x squared, or change in y over change in x quantity squared. Okay, now that's how we write it all if we're doing sigma notation like that with the deltas and things like that. But one thing we learned when we did integrals is that doing an infinite sum like this is the same as doing an integral of this function, but instead of saying delta y over delta x, we would say dy over dx. And again, out here, instead of delta x, we would say dx. And then the boundaries would be from a to b for our function. So all you have to do to find the length of any curve is use this formula right here. You do the square root of 1 plus the derivative of the function squared from beginning to end. So for example, if I want to find the length of sine of x, from 0 to 2 pi. Well, if my function is y equals sine of x, then dy dx is going to be the derivative of that. So it would be cosine of x. So the length of that curve is the integral from 0 to 2 pi of the square root of 1 plus cosine of x squared dx is how I would calculate it. So then, as far as calculating it, you could math 9 that, but this one is actually one we could work through by hand, so I'm going to work it out just so you can kind of see. So this would be 1 plus cosine squared. Well, hopefully, maybe, you remember a trig identity. Actually, no, that's not a trig identity. Ignore that. So you can't do anything to work this out by hand. You cannot square root the both of those and just write it as 1 plus cosine and then integrate because of that addition inside of the expression. So you would have to math 9 in at that point, and to find the actual arc length, it would be 7.640. So that piece of string that I would lay down on this curve and then stretch it out along my x-axis, it would go all the way out to 7.640 on my x-axis. So that's how you calculate length of a curve. Now, the next little part of our notes just kind of goes through that whole concept of chopping up the change in x and the change in y and all that sort of stuff. I'm not going to go into really more detail of explaining that because I feel like I kind of did with the sine of x concept. So as long as your function has a first derivative and your curve is a smooth curve, so it has to be differentiable everywhere within the interval, then you can apply this arc length formula to it. And so this kind of talks about partitioning it. You don't necessarily have to do equal partitions, but it would make sense because ideally we're going to an integral. And so it talks about using the distance formula and then summing those, which would give you the approximate length of the curve. And then transforming that sum from being in sigma notation to being into function notation with our f of prime of x or dy dx is how you want to write it. Now, that does not necessarily have to be done in terms of x. Let's say that you had a curve that, I don't know, maybe it looked like this, and you were trying to find the length of it. Well, you could integrate with respect to y instead of with respect to x to find the length of it as well. Or with respect to time, if your x-axis was a time interval instead of an x interval, whatever. You know, it can be done with respect to any variable, just like all integrals can. Okay, so that's how you end up with your formula for arc length. So that being said, I want to look at another example here. We want to find the exact length of the curve. So that means no calculator on this one. Now, the great thing is that these are really pretty straightforward. They're going to give you the function, they're going to give you the interval, and then all you got to do is plug it into the formula, which means that the first thing you have to do is you have to find the derivative of your function. So that's an x to the 3/2, so its derivative would be an x to the 1/2, but then we would multiply our coefficient times 3/2, and so we would end up with 2 square root of 2 times x to the 1/2, and then minus 1 goes away. So that makes my arc length the integral from 0 to 1 of the square root of 1 plus 2 square root of 2 x to the 1/2 squared. All right, and then we're going to work this out by hand. So the first thing I would want to do is square the 2 square root of 2 x to the 1/2. So 2 squared is 4, square root of 2 squared is 2, x to the 1/2 squared is x. So that becomes 8x. Then, the fun part, why is this not working there, is u substitution. So my u would be 1 plus 8x. Du would be 8 dx. So 1/8 du is dx. So this would become the integral of 1/8 square root of u du. My boundaries would also change to 1 and 9. And then that's like u to the 1/2. So when we integrate it, it becomes u to the 3/2. We do old coefficient divided by new exponent. We end up with 1/12 from 1 to 9. So we have 1/12, 9 to the 3/2 minus 1/12 1 to the 3 halves. So 9 to the 3 halves, we would square root it first, get 3, cube it, and you get 27. So that would be 27 over 12 minus 1 over 12. So you get 26 over 12, or 13 over 6 is the length of that arc from 0 to 1. Okay? So sometimes you have a curve that's not differentiable somewhere in your interval. Like for example here with y equals x to the 1/3, if we're going from -8 to +8, we have a vertical tangent line at x equals 0. So when you have that situation, you can't really, well, you can't apply the arc length formula to it if it's not differentiable on the whole curve. But what if we think about the function in reverse? What if we think about it as x equals y cubed and just switch the variables out, because you can find arc length in terms of y just as you can in terms of x. When you do that though, that also reverses your coordinate pairs. You're basically looking at the inverse, because however long the inverse is how long the original function would be as well. The only thing we need to remember is that we're integrating with respect to y. So your length would be the integral of the derivative of this would be 3y squared. So it would be the square root of 1 plus 3y squared squared. But here's where it's a little bit different. Your boundaries should not be the new points from -8 to +8. You actually want to keep your y's what they originally were there. So that's kind of funky. That's how we deal with the fact that there is a place where we couldn't integrate from before because our function was not differentiable along the whole way. So that becomes the integral from -2 to 2 of the square root of 1 plus 9y to the 4th dy. Now this one you could not use u substitution with, so you would just math 9 that in your calculator. And so 17.261, which means if you go back to the original problem, the length of this is 17.261, like that. Now another way that you could handle a place where it's not differentiable would be to chop it up into the two pieces, or however many there are, to the left of where it's not differentiable and to the right of where it's not differentiable. Like here, for example, we have the curve y equals x squared minus 4 times the absolute value of x minus x, from x equals -4 to +4. You see the graph here. We have a place you can tell very obviously that there's a cusp at x equals 0. So the function is not differentiable there, which means that we're going to have to integrate from -4 to 0, and then from 0 to 4. So that being said, we also have the issue of it being absolute value. So you would need to rewrite that for values less than x and for values greater than x. So your function as a piecewise would be x squared minus 4 times -x when x is less than or equal to 0, and then x squared minus 4 times +x minus x when x is greater than 0. So then your arc length from we gotta find the derivative. So I want you to pause the video at this point actually and see if you can go from there with this piecewise. All right, so you'll see that I consolidated my piecewise to x squared plus 3x and x squared minus 5x. So then when you do the derivative, you get 2x plus 3 when x is less than 0, and 2x minus 5 when x is greater than 0. Then you put them into your arc length formula, one of them going from -4 to 0, and then the 2x minus 5 going from 0 to 4. That's again something you could not integrate by hand. So you would have to math 9 that. When you do that, you add the two pieces together, you get 19.556 for the length of the entire curve here. Now, if you want to give it a try, you could go back to example 3 and try doing example 3 the same way, where you would integrate it from -8 to 0, and then from 0 to +8, and put them together and see if you get that 17.261, like we did by changing what we were integrating with respect to. Also, you have 2 AP practice problems at the bottom of your notes that I would like for you to give a try before I see you again.